Welcome to G Fun Facts Online. Today, we are stripping away the history of body art to look at its future. For thousands of years, the tattoo has been a static medium. Whether it was a mark of identity, a memory, or an act of rebellion, it was always the same thing: ink, etched into the dermis, sitting there permanently. It was art, but it was passive. Right now, we are witnessing a metamorphosis. We are moving from the age of ink to the age of information. We are talking about the optical tattoo. This represents the absolute convergence of biology, photonics, and electronics. It is a technology that doesn't just sit on the skin. It functions with the skin. And to be clear, this is not science fiction. This is happening now, driven by breakthroughs in epidermal electronics, photonic skins, and biocompatible optical waveguides. Researchers are currently printing circuits directly onto human skin, circuits that can monitor glucose, transmit high-speed data using light, and control machines with a flick of the wrist. We are going to explore the comprehensive landscape of this technology, the physics of how it works, the incredible engineering behind printing it, and the revolution it signals for healthcare and human capability. To really understand the optical tattoo, we have to start by distinguishing between the two primary technologies that are fighting for real estate on your arm. On one side, you have electronic skin, or e-skin. On the other, you have photonic skin. Most people have heard of e-skin. It relies on the flow of electrons, just like the wiring in your house or phone. The goal of e-skin is to mimic the mechanical properties of human tissue. It needs to be stretchable, soft, and curvilinear. It embeds conductive sensors to measure electrical signals, things like your heart rate via ECG, muscle activity via EMG, or brainwaves via EEG. It is essentially a flexible circuit board. But photonic skin is different, and this is where the true optical breakthrough happens. Instead of metal wires conducting electricity, photonic skin uses optical waveguides. Think of these as microscopic channels that guide light, similar to how fiber optic cables work under the ocean, but on a microscale on your body. Why use light? Because light is immune to electromagnetic interference. In a hospital or an industrial setting, there is a lot of electrical noise that can mess up traditional sensors. Light cuts right through that. Furthermore, by using light, photonic skins can measure biochemical markers that electricity struggles to detect. They can use spectroscopy, analyzing how light interacts with matter, to check the molecular composition of your sweat or blood flow with extreme precision. So, the optical tattoo is the fusion of these domains. It is a bio-integrated device that uses light to sense and transmit data, printed with materials that are mechanically invisible to the wearer. Now, let's talk about the hardest part of this entire endeavor: fabrication. How do you print a computer onto a human? The greatest challenge here is the substrate. In traditional electronics, we use silicon chips. Silicon is rigid and brittle. Human skin is the opposite. It is soft, textured, wet, and constantly moving. Plus, your skin sheds its outer layer every few weeks. You cannot just glue a rigid chip to a flexible, shedding surface. Engineers have had to develop 3 specific methods to turn the human body into a printed circuit board. The first method involves lasers and graphene. This is known as laser scribing. Researchers at institutions like Tsinghua University and the University of Texas at Austin have pioneered this. Here is how it works. You apply a precursor material, like graphene oxide or a specific polymer, to the skin or a transfer paper. Then, you use a precise laser to scribe a pattern. The heat from the laser causes a chemical reaction that reduces the non-conductive oxide into highly conductive graphene. This creates a graphene electronic tattoo, or GET. These things are mere nanometers thick. They are about 85% transparent, so they are almost invisible. They are breathable, which is crucial for skin health. And the coolest part, they don't use glue. They adhere via van der Waals forces. These are the same molecular attractions that allow geckos to stick to walls. It creates a bond without any adhesive or needles. The second fabrication method is aerosol jet printing. This solves a major temperature problem. Traditional printing requires high heat to sinter or melt together conductive inks. If you tried that on a human, you would burn them. Engineers at Duke University developed a solution. They created a silver nanowire ink that stays conductive without needing that high temperature baking. They use an aerosol jet printer to spray this ink directly onto the skin. It creates a mesh of nanowires. Because it is a mesh, it maintains conductivity even when you stretch it. They demonstrated this by printing leads on a pinky finger and connecting them to an LED. The light stayed on even as the finger bent and flexed. This is a game changer for medicine because it allows for rapid prototyping. A doctor could technically print a custom sensor array around a patient's specific wound or joint in minutes. The third method is about taking this out of the lab. It is called the body printer. This is a portable, wearable plotting machine that straps directly onto the limb. It automates the deposition of conductive inks onto the skin, and it actively adjusts for the curvature and movement of the body while it prints. This democratizes the technology. It suggests a future where tattoo parlors might just be automated kiosks. You walk in, stick your arm in a machine, and it prints digital functionality right onto you. Let's move deeper into the architecture, specifically the optical part. We mentioned waveguides earlier. This is arguably the most powerful feature of these tattoos because it allows for optical wireless communication. Think about implantable medical devices, like pacemakers or neural chips. Right now, they typically use radio frequency, or RF, to talk to the outside world. But RF is slow, it consumes a lot of power, and it is prone to interference. The optical tattoo acts as a high-speed data gateway. It uses near-infrared light. This specific type of light can penetrate skin and tissue with very minimal absorption. This allows data to be transmitted from an implant inside your body to the tattoo on the surface at rates that far exceed Bluetooth. We call this a transdermal optical link. It ensures that neural data or cardiac rhythms are offloaded instantly. And it is secure. A radio signal broadcasts in all directions and can be hacked. A light beam is directional. If you aren't in the line of sight, you don't get the data. But to guide this light, we need wires, and we cannot use glass fibers. We need something biocompatible. Scientists have synthesized waveguide from silk fibroin, which comes from silkworm cocoons, as well as hydrogels and biodegradable polymers like PLA. Silk waveguides are incredible. They are optically transparent and biodegradable. Imagine a scenario where you have surgery. The doctor prints a silk optical tattoo to monitor the site for infection. Once the wound heals, the tattoo just harmlessly dissolves into your body. We also have hydrogel fibers. These mimic the density of your own tissue. If you functionalize them with specific chemicals, they can change their refractive index when they encounter glucose or oxygen. That means the fiber itself changes how light passes through it based on your health, effectively acting as a sensor and a wire at the same time. Not all of this data needs a computer to read, though. There is a project called Magic Ink from the University of Colorado Boulder that focuses on visual biosensors. These use photochromic microcapsules. Basically, it is tattoo ink that changes color when exposed to specific stimuli. Think about UV detection. You could have a tattoo that is invisible under normal light, but if you go to the beach and are exposed to dangerous levels of UV radiation, the tattoo turns bright blue. It is a permanent resettable sunburn warning. Or consider diabetics. You could have inks that shift from green to brown as blood sugar rises. It gives the user a glanceable interface for their health. No needles, no smartphone app, just looking at your skin. So what does this actually look like in practice? The applications are revolutionizing three main areas: medicine, human-machine interfaces, and photomedicine. In the medical revolution, the killer app is continuous glucose monitoring. By combining electrochemical graphene tattoos that analyze sweat with optical sensing, we get a non-invasive closed loop for diabetes management. No more finger pricks. Then, there are smart bandages. Imagine an optical tattoo printed around a wound. It monitors temperature, which is a sign of infection, and oxygenation, which is critical for healing. If the sensors detect an infection, the bandage could trigger a heat release mechanism to deploy antibiotics stored in a hydrogel layer. It treats you automatically. In neonatal care, this is heartbreakingly useful. Premature babies right now are covered in wires and rigid sensors. It damages their fragile skin and makes it hard for parents to hold them. Epidermal electronics offer a wireless NICU experience. A virtually weightless tattoo can monitor vital signs without restricting movement or parental bonding. Next is the human-machine interface. We are talking about silent speech. By placing graphene tattoos on the throat, sensors can detect the tiny muscle movements and vibrations of the larynx. This allows for subvocal communication. You could control a computer or speak on a phone call by merely mouthing the words. The security applications are immense, as are the benefits for people with speech impairments. We also have drone and robot control. High-density EMG tattoos on the forearm can map individual finger tendons. You could control a drone or a robotic arm with intricate hand gestures, removing the need for joysticks or keyboards completely. Finally, photomedicine. Utilizing those waveguides we discussed, optical tattoos can deliver precise wavelengths of light to deep tissue wounds. This activates light-sensitive glues that bond tissue together. We are literally using light to stitch a wound closed. There is also optogenetics. For patients with neural implants, optical tattoos can serve as the external interface. They deliver the specific light pulses required to stimulate or silence neurons in the brain, which is a frontier treatment for conditions like epilepsy or Parkinson's. However, we have to be realistic. There are significant challenges before everyone is wearing an optical tattoo. First, power. You cannot plug a tattoo into a wall socket. Current solutions involve NFC, near-field communication, where you hold a phone near the tattoo to power it inductively. But the future is biobatteries. We need tattoos that harvest energy from the lactate in our sweat or the thermal gradient of our skin. Second is privacy. When your skin becomes a data transmitter, who owns the signal? An optical tattoo broadcasts your heart rate, your stress levels via skin conductance, and your location. It creates a biometric fingerprint. Securing these body area networks with encryption is a critical area of research. And third is durability versus physiology. Skin is a hostile environment. It stretches, sweats, and exfoliates. While graphene is durable, your skin sheds. So a surface tattoo is temporary by design, lasting maybe 1 or 2 weeks. The industry has to decide, do we go for low-cost, disposable daily tattoos? Or do we develop semi-permanent subdermal solutions that sit just below the exfoliation layer? In conclusion, the optical tattoo is more than just a wearable. It is the dissolution of the device. It represents a future where technology is not something we carry in our pockets, but something we are. By printing biocircuits and optical waveguides directly onto the skin, we are effectively upgrading the human operating system. From the diabetic child who no longer needs to prick their finger, to the surgeon controlling a robotic arm with a gesture, to the everyday user warned of UV exposure by a glowing mark on their wrist, the optical tattoo promises a world where the boundary between the biological and the digital is not just blurred, but erased. The ink of the future is alive, and it is lighting the way forward. Thanks for listening to Fun Facts Online.